So I'm now on page 11, and on page 11 it talks about modeling, and that you're going to see what happens with some exponential equations. And it kind of leads into what we're going to be talking about also today. Modeling the spread of a flu at a high school. Mike is sick with a flu, but he still comes to school on Monday. Ooh, this was definitely before COVID. He arrives at 8 a.m., and by 9 a.m., which is hour 1, Mike has infected 2 of his friends. This is COVID. Not before COVID, it is COVID. Okay? By 10 a.m., hour 2, Jose is okay, and it keeps on going. So for me, and I could see something like this on an EOC test, is let's look at what's happening. So here's Mike, and here's hour 0. He has it. By hour 1, he has infected 2 of his friends, Jose and Lisa. Okay, that's hour 1. By hour 2, Jose has infected Bill and Ted, and Lisa has infected her friends Jenny and Kiara. Okay, that's hour 2. So hour 2, so see where they're getting this. Hour 1, hour 2, hour 0, hour 1, hour 2. Okay, so then by hour 3, each of these are going to infect somebody. How many is that? That's 8. Do you see the pattern yet? So I'm going to double this, I'm going to double this, I'm going to double this, I'm going to double this. Okay, see what's happening? And this is kind of what happened with COVID, unfortunately. When someone got infected, it just actually spread quicker than this. But you get the idea. Okay, so now let's plot that and see what happened. So at hour 0, we were at 0. Hour 1, what am I saying? Okay, hold on a second. So let me look at my graph again. So this is hours in school. So this is going to match up with hours 0, 1, 2, 3. But look at this. There's 10, 20, 30, 40. So when we talk about one student, we're just going to be right down here. And then by hour 1, that's hour 0. Hour 1, we had 2. Hour 2, we had 4. By hour 3, we had 8. Hour 4, we had 16, so there's 20, so 16. Hour 5, we had 32, there's 30, and then a little above that. Well, not that much above, how about right there? Okay, hour 6 is 64. Hour 7 is 128. See how quickly this grows? Okay, what's hour 8? So there's hour 7. You can see those points. Hour 8 will double it again. It's 256. So at hour 8, we are off the chart, like way off the chart. Okay, so that's what was happening, is it was just growing so quickly that by hour 8, we were off of there. Okay, so by the time they left at 3 o'clock, they were just like a lot of the school. So now what it says is, if the school has 1,000 students enrolled, what percentage of the student body has a flu by 3 p.m.? Well, that is hour 8. Hour 8 is 3 p.m. Because here's hour 8, 9, 10, 11, 12, 1, 2, 3. 1, 2, 3. 8. No. 8, 9, 10, 11, 12, 1, 2, 3. Hold on once again. Okay, sorry, I had to just go back to do the reading again. It says he arrives at 8, and by 9 a.m., which is hour 1, so it's 9, 10, 11, 12, 1, 2, 3. So here is 3 p.m. So if I want to find out what percentage of the student body, well, there's 128 out of 1,000 that are infected, and when I divide, okay, I'm going to get 12.8. I'm going to get, I should do all the work, 0.128. So as a percent, that's 12.8%. By 3 p.m., 12.8%. If they would have been there one more hour, it would have been 25.6%. So you can see it goes up very quickly. Okay? Just wanted to show you, because these are kinds of the problems that you might see on this. And I'd love to have you try this one on your own. We're going to pause and have you do this one. Answer at least the first couple questions. A and B, fill out the table for what's given, and then A and B. Okay, go. So it doubles every week. So 3,000, 6,000, 12,000. Okay, you got that. So how many will we have after 2 weeks? 12,000. After 5 weeks, 96,000. Okay, now, how many will we have after X weeks? Well, notice that it's doubling. Okay, you start with 3,000, but every time we're going to multiply by 2 to the X power. Okay, this tells me I'm going to double. This tells me how often I'm going to do it. So this is going to be, so if you look at it, if you put in a 0, if you put in a 0 right here, that'd give me 1. 1 times 3,000, sorry, I forgot a 0. I get 3,000. Then if I have 6,000, I put in a 1 here. That'd be 2 times 3,000. Okay, so you can kind of see. We're going to talk about that right now. That's the reason I wanted you to see how you come up with this. When we get into exponential growth, it will become a little more clear. If we begin with 3,000, after how many weeks will we have 24,000? Okay, now the amazing part on that is that I don't think we can do that just yet because it requires us to solve, and we have to come up with an exponential. You haven't learned how to do that yet. So anyway, I want you to see where this comes from, and we're going to talk more about this right now with exponential growth. Okay, so turn to the next page, which is page 13, exponential growth note. The exponential function is equation with a variable in the exponent. So, and a quantity grows by a fixed percent at regular intervals. And an exponential growth is going to look like this because it's going to grow, and it's going to grow exponentially. So an exponential growth is going to look like this. Okay? So, and you'll see that more as we write the equation. So the equation is y is equal to a times 1 plus r to the x. The constant a represents the original amount. So a is the original amount. What do we start with? Original, or sometimes we'll call it initial amount. R represents the rate, the growth rate. Well, it represents the rate, but we have a plus, so therefore it's a growth rate. Because it's a plus, it's a growth rate. And it's going to be expressed as a decimal. So they're going to give us a percentage, we have to change it to a decimal. The variable x represents the number of intervals. Number of intervals. How often does it happen? Or the time periods of growth. And that A is the initial amount, just like we had the cicadas, that was the 3,000. The variable y represents the amount after x intervals of growth. So how much is there in it? So we're going to look at the equation so that we can identify what's happening. So if this is my equation, it can be used to model the average salary in thousands of dollars, so average salary in thousands of dollars for a Major League Baseball player in the United States each year since 1984. Okay, so pay attention to those. So write the equation in this form. Well, notice we have 1.2, and that rate is going to be a decimal. So this can be rewritten as y is equal to 283 times 1 plus 0.20 to the x. Okay? What is the growth rate? Well, the growth rate is 0.20, but we're going to write it as a percent. With a percent, you move the decimal point 2 places, so it's 20%. What does the number 283 represent in this equation? Well, it's the initial amount, which is a salary in thousands of dollars. So this is the initial amount of a salary, so it's 283,000 because it's in thousands of dollars. Okay, that's the average salary of a Major League Baseball player each year since 1984. Okay, we don't know how many years, but that would be the average salary since 1984. Okay, what does the variable x represent in this equation? It's the number of years. That's the time period. So the years since 1984. 1984, I know. Long time ago. I graduated high school in 1983, so yeah, pretty long time ago. Suppose you substitute the value 1 in for x in this equation. What value do you get for y? What does this represent? So let's do it. Let's plug that in. So if I plug it in, y is equal to 283 times 1.2 to the first power. Take out your calculators. And you get 339.6. We want this in thousands of dollars. So $339,600. Okay? And 1 is 1 year past. So 1 year past 1984. So this would be the average salary. 1 year past 1984 is in 1985. Because we put a 1 in, that's 1 year past. Estimate the average salary in 1994 for a Major League Baseball player. Okay, so how many years since 1984? That'd be 6. So x is equal to 6. So we plug that in. Y is equal to 283 times 1.2 to the 6th power. Take out your calculator. 1.2 to the 6th power times 283, and we get 845.0334 blah 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 blah. Okay, but we're going to do it in dollars and cents, and we're going to round it. So I should put that dot right there. So as you can see, we're going to go, this is going to become dollars, so $845,033, because I'm moving my decimal point to thousands, and 47 cents. I doubt if that 47 cents is going to make a big difference if you're making $845,000. Wow! That's the average salary in 1990 of an baseball player. And we're in 2022, so you know it's huge. What assumption do you make when you use this equation to make a prediction like the one in number 6? Well, a couple things. One, that we assume that the average is going to go at a constant rate and fixed by a fixed amount. Well, we know that doesn't happen because depending on the player, okay, it's going to shift it around. But our assumption is that the salary grows by a fixed amount and that there was no additional raises or bonuses or anything else. Okay? Questions? Oh, you're not with me. Sorry. So let's look at your homework. This first part, it just says find the value of y when x is equal to 4. Round your answers to the nearest hundredth. So you can figure that out. It's just going to plug that in. This one, suppose you open a savings account with $100. The account has an annual interest rate of 5%. Assume there are no deposits or withdrawal. Answer to the nearest cent. And so it just asks you to step through it. 8 and 9, it gives you a model. It's talking about the years. Find the population in 1980. Okay, find the population in 1990. So just pay attention. After the year 1980, how many years after is this? How many years after is this? Okay, so just think through those. Okay, let's go to the next page. And it wants you to write the equation of the population, of going through it. So I'm just going to do a couple of these with you. A pond has a fish population of 250 that increases by 12% each year. Write an equation. So remember our general form, y is equal to a times 1 plus the rate to the x power. So what does the 250 stand for? Well, that's the initial amount. Okay, then 1 plus the rate. My rate is 12%, so that's 0.12. So that's 1 plus 0.12 to the x. So my equation is y equals 250 times 1.12 to the x power, right? What will the population be in 5 years from now? So what are you going to do with that? Exactly, plug 5 in here. So you're going to go y is equal to 250 times 1.12 to the 5th power. Pull out your calculator. And you're going to get a number that you're going to probably want to round. And think about it. Fish. Can you have a portion of a fish? Well, that's gross. But yes, you can. But we're going to look at whole fish. And we're going to say that it's approximately. And these little symbols right here, I don't know if you can tell what I'm writing. Okay? They're like wavy equal signs. That means approximately 440 fish. Okay? And you'll do number 10. Number 11. It's doing that same kind of thing. Here's my rate, And in 2001, this is my population. Write an equation to give the number of people in 2001. Estimate the population in 2008. So how many years past 2001 is this? So write your equation. Okay, so I'll help you. Y is equal to my initial amount of 19,000. What's my rate? 0.02. So 1 plus 0.02 to the x, or y is equal to 19,000 times 1.02 to the x. Okay, estimate the population in 2008. Well, how many years? Right, so x is going to be equal to 7. Hey, and remember these are people. People are people whether they're a whole or a partial, so make sure you give the whole number of people. Now this says, what was the population in 1995? Assuming there's a growth rate that is fixed. So I'm going from 2001, 1995, what did I do? I went back, so I have a -6. So you can approximate that. Okay? So I'll let you do those other ones for homework. If you have any questions, you know where to find us. Thank you so much.